Welcome to my talk for our paper Rich Specifications for Ethereum Smart Contract Verification. My name is Marco Eilers and this is joint work with Christian Brehm, Peter Müller and Robin Sierra from ETH and Alex Summers from UBC. So first of all, what is a smart contract? Well, smart contracts are programs that are executed inside blockchains like Ethereum, for example. So this is a simplified example of a smart contract, which is a very common use case. It implements its own kind of currency, usually called a token. So the contract has a map that has the balance of each other contract in the blockchain of this new token currency. And it has a function, for example, that transfers tokens from the caller of the function to some other address by just updating the balances in the map. So if you think about it, this looks a lot like a standard class in a normal object-oriented programming language, right? We have fields, we have methods that modify those fields. But there are some important differences, in particular when reasoning about smart contracts versus reasoning about standard object-oriented programs. So first of all, smart contracts generally execute in an untrusted environment and they have to typically call unknown other contracts. So in this case, we have to call this notify function here on some address that we get as a parameter. We don't know who that is. We don't know if we can trust them, what they do. They are not verified. We can't assume that. So this is challenging for verification because it rules out many standard reasoning techniques. For example, standard separation logic assumes that all executing code is verified, so that just wouldn't apply in this setting. Second of all, the execution model or language model is somewhat different. So we have stronger encapsulation. In particular, the fields here cannot be modified by any other contract, only by the code of our own contract. And second, every function can inspect who called it. So it can do this by reading this message.sender field, which contains the address of the contract that called the current function. And so, for example, the transfer function uses this to always transfer tokens away from the caller to someone else. And finally, whereas standard object-oriented programs can be used for anything, smart contracts typically are used for modeling something like actual contracts, so in particular resources and resource transfers, like our example here, which models its own currency. So in this paper, we provide a sound, modular, and precise verification technique for collaborating smart contracts using intuitive domain-specific specifications. So in particular, our technique is sound, even in the presence of arbitrary callbacks. And I'll explain in a second why this is important, but this is unlike many existing verification techniques. We show how to reason about multiple contracts that together implement a distributed application and do so in a contract modular way. So we verify each contract only using interface abstractions of the other contracts it interacts with, unlike existing techniques. And finally, we provide domain-specific specifications that allow users to directly specify desired behavior in terms of resources and resource transfers, and the resulting verification technique is able to catch typical errors by default. So let's look at the first point, and that's sound reasoning in the presence of arbitrary callbacks, or also called re-entrant calls. So I'll illustrate this on a simple example here. We have a contract that just has an accumulator field and two functions that both add values to the field and perform a call to the outside. So let's see what happens when foo is called. So we add 2 to the accumulator, and now we call notify on message.sender. Message.sender is whoever called us, so that could be anyone, literally. So we don't know who it is, we don't know what their code is, we don't know what they're going to do. But we call notify on that, and now that can do literally anything, right? In the bounds of the language. So for example, what it can do, it can perform a callback or re-entrant call and call bar. And now bar will add 8 to the accumulator, perform another call to the outside. Let's skip that for the moment. And add 10, then return. And let's say after that, notify returns. So the point is, after the call to notify, our state can have changed. And if our contract isn't written to expect that, then we can have a bug. So these are called re-entrancy bugs and are the source of many, if not most, smart contract security problems. So now the problem is, if I try to reason about this soundly, I don't know which call I'm calling. How can I know anything, or what can I know about my own state after the call to notify? The thing is, this other code, I don't know what it's doing. It could call me back 0 times or an arbitrary number of times with arbitrary arguments, whatever. But we do still have the language guarantees that say that our accumulator can only be directly modified by our own code. So if ACK is modified, then this has to be via one or several re-entrant calls from the code that we're calling. And because of this, because we get this guarantee from the language, we can actually find out something about what our state can look like afterwards just by knowing our own code without knowing anything about the code that we're calling. So in particular, we can look at what we call the local segments of our contract. So that are the segments of the code that are not, or segments of our code between calls to external functions. So it's just this, then these two lines, and then this. They're always calls in between, as you see. And as we see here, each of those local segments only adds something to the accumulator, and they all add even values. So if we can write this down, every local segment, at the end of every local segment, we have an even value in the accumulator, assuming it's even in the beginning, and its value will now be greater or equal than it was at the beginning of the local segment. That's true for every segment in our contract. And so we call this a segment constraint. And if we've proved this for every local segment in our contract, now this can tell us something about the effect that the call to notify can have. Because notify can only manipulate or change our state by executing some number of local segments. So whatever the effect is, it'll be within the reflexive transitive closure of the segment constraint. So afterwards, we know that the value of the ACK will still be even, and it will be greater or equal than the value it had before the call. And we can use this information, for example, to prove a precise post condition for foo that says at the end, the value of the accumulator is even again, and it's at least 6 more than at the beginning of the function, but possibly more. And without knowing anything about the code that we're calling, this is the most precise specification we can actually prove. So this is an example where segment constraints allow us to prove something about the effect of calls. So we can know something about the effects of calls, even though we don't know who we're calling, just by looking at our own code, because we get this encapsulation from the language. But segment constraints are also useful in other scenarios, where they can be used to express properties that are independent of calls in general. So let's again look at the token contract from the beginning. So if I'm a client of this token contract, one important property that I want is that nobody else can just take my tokens away. So in other words, since conceptually my balance belongs to me, I want that only I can decrease my balance. Others can increase my balance by just transferring tokens to me, but only I should be able to decrease it. But this is another property which we can just prove it for every local segment of the contract. And if it holds for every local segment of the contract, then it holds in general. Right? If every segment of the contract only ever decreases the balance of the caller and not of anyone else, then it's impossible to do this in general. So we can express this as a segment constraint again and prove it in general, and then we know that it holds in general, and we didn't have to reason about calls at all. In the paper, we show how this idea can also be used and expanded to verify multiple collaborating contracts in a modular way. If you're interested in that, have a look at the paper. I'm not going to go into this now. So finally, let's look at those domain-specific specifications that I've mentioned. So tokens here are resources. This is an example, a typical example in that it's the contract that deals with resources and resource transfers. Now, for almost any such contracts, there are some basic properties that you basically always want. So for example, some basic resource properties that tokens, in this case, resources in general, can't be arbitrarily duplicated, otherwise they'd be worthless. That we have ownership guarantees like nobody can take away my tokens, nobody can destroy my tokens. So you can specify these and prove them separately, but you need them all the time, really, which is why we provide direct support for proving these properties automatically. So what we allow users to do is to specify, well, there is something like a resource called token that should behave like a resource and have all these properties. And slightly simplified, we say that the balances of these tokens are represented in self.balances in this map here. And now what our technique will do is it will only allow the balances field to be changed in ways that are consistent with these basic properties. So in particular, now there are only a specific number of changes that are allowed on this resource state. namely a set of resource operations. So the resource state in particular looks like this. Everybody has a balance. A has 3 of these yellow resources and B has 0 at the moment, let's say. And resources are stateless things. You just have some number of them. At most, they have an identifier. So now the simplest thing I can do, perform a transfer operation. So A can transfer 2 of its resources to B. So this makes nothing is duplicated in this state, right? We still have 3 resources at the end. And importantly, we make sure that ownership properties are respected by saying only A is allowed to perform such a transfer. So that's the most basic resource operation. Resources can also be created, but only by especially by privileged addresses called minters. And resources can be destroyed only by their current owner. So A can, for example, destroy 2 of its own resources. So these and some others are the basic resource operations that all preserve these basic properties that we want. And now if I have a function like transfer here, which manipulates the balances of my resource, then I need to now justify why this change is okay by providing a resource operation that conforms to these changes here. So in this case, I would say, well, I'm performing a transfer resource operation here on the token resource. And then our verifier can check whether this change that has been made to the balances actually corresponds to performing a transfer and if the transfer was allowed. So for example, if the current caller was allowed to perform this transfer to guarantee the ownership principle. And now that we have this, we can also use this to specify the behavior, the functional behavior of our transfer function by, for example, saying, well, it performs a transfer operation of tokens from to amount. This is more intuitive and much simpler than describing what this transfer function does in terms of the balances map, right? Some balances increase, some decrease, and all others stay the same. This is much shorter. So this is the basic idea. We have some more advanced resource operations. For example, you can make offers. The idea is that you agree to some exchange being performed later. This is useful to be able to model deferred payment operations that are very common in smart contracts. Not going to go into the details here. We also have some more advanced concepts like, for example, derived resources, which are resources that represent the right to get back a different resource. So we have implemented our concept in a tool called 2Viper, which is an automated SMT-based verifier for Ethereum smart contracts written in the Viper language, spelled with a Y. And 2Viper is implemented on top of the Viper verification infrastructure, spelled with an I. So the tool is open source, available on GitHub, and also submitted as an artifact. Finally, we've evaluated our approach on a number of challenging real-world examples. So ERC20 is the most basic token contract that's used everywhere. Of course, we can verify that, but we can also verify a more advanced version of this, which, for example, intentionally uses callbacks and re-entrancy as part of its intended workflow. So this is something that other verification approaches that restrict re-entrancy wouldn't be able to do. We've verified some applications that consist of multiple contracts, and we've done this in a contract modular way, as I've said. And finally, so Uniswap, for example, is an important big real-world contract, and we were able to concisely and intuitively specify its entire functional behavior in terms of resource operations. Right, with that, I am finished, and I'm open to answer your questions. Thanks for your attention.